Hello and welcome back. Today we are going to talk about our new chapter. It's about higher order ODEs, higher order equations. In the last chapter we discussed about first order. Now we are going to talk about higher orders. So what we are going to do is we will start with order 2 and then we will see that the concepts from n equal to 2, the order equal to 2 to higher orders can be extended very naturally, and we are just going to discuss about the linear equations. So let's start with the order 2. So we are going to discuss second order linear equations. This we can say is our first topic of discussion, first section. So to start with, let's see the journal form. So the journal form for second order linear equation is a2x y double prime, by y double prime we mean the second derivative, plus a1x y prime plus a naught x y equal to fx. This is f of x. Here the functions a2x, a1x, a naught x and fx are any function of x. Okay, and then let's define homogeneous equation. So we defined homogeneous of equation in our chapter 1 also. So here I am just going to recall it for the second order. Homogeneous equation means our fx is equal to 0. So this equation we will call the homogeneous equation. Simply our fx is equal to 0 means we don't have any term which doesn't involve any dependent variable or its derivative. And if equation is not homogeneous, then we will call it non-homogeneous. Okay, so now we know what we mean by homogeneous and non-homogeneous equation. So non-homogeneous means it's not homogeneous. Okay, fair enough. You must have observed, but the definition for higher order homogeneous and for the first order homogeneous is different. For the first order, we said an equation is homogeneous if it is of form dy over dx plus pxy equal to some function qx. That was our definition for homogeneous in first order ODEs, but here the definition is little bit different. We will say if fx is equal to 0, then our equation is homogeneous. Okay, so let's move forward. So if you have two solutions, so this what we are going to discuss now is also known as superposition principle. Superposition principle for homogeneous equations. And we say if we have two solutions for homogeneous equations, or any number of solution in general, but we are starting with 2. So if we have two solutions, if y1 and y2 be two solutions of a homogeneous equation, then any linear combination means C1 times y1 plus C2 times y2, any linear combination is also a solution. And this is very easy to verify. You can just plug in your y, which is C1 y1 plus C2 y2, in your original equation, and you will see that y is a solution. So it's very easy to verify, and I'm leaving that for you. Okay. Next, we are going to talk about what it means to say the functions are linearly independent. And we are starting with two functions only, but later towards the end of this chapter we are going to generalize all the definition and all the terminologies. So what it means to say that two functions are linearly independent. So we will say f1 and f2 are linearly independent if we have a linear combination of f1 and f2 which is 0, means c1 f1 plus c2 f2 is equal to 0, implies c1 and c2 both are 0. It means there is no non-zero linear combination, like there is no non-zero c1 and c2 which can make this combination equal to 0. Or in simple terms, we can also say that f1 or f2 is not a constant multiple of other, like f1 is not a constant multiple of f2, or f2 is not a constant multiple of f1. Okay, it's always to see some examples, right? So let's see some examples. So first we will see two functions, say sin x and cosine x, and we want to check if these functions are linearly independent or not. So what we will do is we will take the linear combination. So c1 sin x plus c2 cosine x equal to 0. If somehow we can prove that c1 and c2 are equal to 0, then we will say sin x and cosine x are linearly independent. If we can find out some c1 c2 non-zero such that this combination is equal to 0, then they are linearly dependent. Okay, let's try to prove this. So if we substitute x equal to 0, so by any way we want to prove that c1 and c2 are not equal, are equal to 0 if we want to prove the linear independence. So if we substitute x equal to 0, what will we get? We will get c1 sin 0, which is 0, plus C2 cosine 0, which is 1, equal to 0. Means C2 is equal to 0. Okay. So if C2 is equal to 0, we have C1 sine x is equal to 0. If you substitute, say, x equal to pi by 2, then sine x is 1, and that gives us C1 equal to 0. Right. So we proved C1 equal to 0 and C2 equal to 0. It means, so that implies, this notation, by the way, is for implies sine x and cosine x are linearly independent. Let's see one more example. Say e to the power x and x times e to the power x. The technique is the same. We set a journal combination c1x plus c2x e to the power x equal to 0, and if we can prove that c1 and c2 are equal to 0, then these two functions are linearly independent. Okay. So this here I see this is x times e to the power x. If we substitute x equal to 0, the second term is going to be 0. So if we substitute x equal to 0, c1 e power 0 is 1 plus c2 times 0 equal to 0, which gives us c1 is equal to 0. So we have c2x times e to the power x is equal to 0. Proving c2 equal to 0 is very easy. You can substitute any value of x other than 0. Say we substitute x equal to 1. So we will get c2 e power 1 equal to 0, which implies c2 equal to 0 or e equal to 0. E is not equal to 0 means c2 is equal to 0. So we proved c1 equal to 0, c2 equal to 0. So e power x and x times e power x are linearly independent. So similarly, try to prove that e power x and e power negative 2x are linearly independent. These two are linearly independent. Oops. That's your exercise. Okay. Sometimes checking if two functions or a set of functions are linearly independent or not is difficult, but we are in ODEs, and in ODEs it's very easy to check using the Wronskian. So for that, let me define what is Wronskian. So let's define Wronskian. So we define the Wronskian of two functions, say y1 and y2, as the determinant of first row we keep y1 y2, in the second row we take the derivatives. First derivative of y1, first derivative of y2. This is the Wronskian. And determinant we calculate by we multiply the diagonals. So y1 times y2 prime minus we multiply the off diagonals, y1 prime times y2. This is our determinant. Okay, let's see one example. So we are going to calculate the Wronskian of sin x and cosine x. Okay, so in the first row we keep them as it is, sin x and cosine x. In the second row we write the derivative. Derivative of sin x is cosine x, derivative of cosine x is negative sin x, which is equal to, we multiply the diagonals, we get negative sine square x minus we multiply the off diagonals, so we get cosine square x. If you pull out the negative sign, we have sine square x plus cosine square x, and we know that sine square x plus cosine square x is equal to 1, so the Wronskian is equal to negative 1. Okay, so calculating Wronskian of two functions is very simple. How we can relate this Wronskian and the linear independence we will see now. So let's see how this Wronskian and linear independence are related. Oh, before I forgot, I just forgot to say, linear dependent means something is not linearly independent. Okay, so we talked about linear independence, and if two functions are not linearly independent, we will say they are linearly dependent. So how Wronskian and independence are related? So suppose we have two solutions, y1 and y2. These are solutions of homogeneous second order linear ODE. Then if y1 and y2 are linearly independent, then the Wronskian of y1 and y2, which we already saw before how to calculate, is not equal to 0 at all the points. And if y1 and y2 are linearly dependent, then Wronskian of y1 and y2 is going to be 0 at all the points. Okay, So this is how we can check if y1 and y2 are linearly independent or not using the Wronskian. Very simple. Okay. So in the next video we are going to talk about the solutions of homogeneous equation, linear homogeneous equation of the second order ODEs, and we stop here for this video. Thank you. Bye bye. See you.